Every time you ask ChatGPT a question, or an AI labels a photo, or a self-driving car decides to brake, the same fundamental unit is doing the work. It's called an artificial neuron. This is how AI actually works. Over 10 parts, we're going to build up from a single neuron all the way to the large language models powering today's AI. Let's start at the very beginning. The idea starts with biology. Your brain has about 86 billion neurons. Each one receives signals from other neurons, processes those signals, and decides whether to fire its own signal forward. That's it. Receive, process, fire, or don't fire. In 1943, Warren McCulloch and Walter Pitts asked a simple question. Can we build a mathematical version of this? Not a perfect replica of a brain cell, but something that captures the core idea. Take in some numbers, do a calculation, and output a decision. That's the artificial neuron. A real neuron is far more complicated than this. Thousands of connections, electrochemical signals, behavior we still don't fully understand. The artificial version throws all of that out. It keeps just the math, weighted inputs, a threshold, and an output. One equation. Let's build one. Say you're trying to predict whether a student will pass an exam. You have two inputs, hours studied and hours slept the night before. These are just numbers. Hours studied might be 6, hours slept might be 7. Those numbers feed into the neuron, but not all inputs matter equally. Studying for 6 hours probably matters more for passing than sleeping 7 hours. So each input gets multiplied by a weight. A weight is just a number that controls how much that input influences the output. A high weight means that input matters a lot. A low weight means it barely matters. Inside the neuron, all the weighted inputs get added together. 6 times 0.8 is 4.8. 7 times 0.3 is 2.1. Add them up, 6.9. This is called the weighted sum. But there's one more piece. The neuron also has a bias. Think of it as the neuron's baseline tendency. A positive bias makes the neuron more likely to fire. A negative bias makes it harder to fire. It shifts the decision threshold up or down. If our bias is -3, the total becomes 6.9 minus 3, which is 3.9. We have 3.9. But that raw number isn't very useful as a prediction. Is 3.9 a pass or a fail? We need something to convert this into a decision. That's the activation function. It takes the weighted sum plus bias and transforms it into something meaningful. The simplest activation function is the sigmoid. It squashes any number into a value between 0 and 1. Feed in a large positive number, you get something close to 1. Feed in a large negative number, you get something close to 0. Feed in 0, you get exactly 0.5. Our 3.9 goes in, and out comes 0.98. That's a 98% chance of passing. So that's the whole thing. A neuron takes inputs, multiplies each by a weight, adds them up, adds a bias, and passes the result through an activation function. Inputs times weights plus bias through activation. Every artificial neuron in every AI system works this way. But the neuron doesn't know those weights ahead of time. Nobody sits down and decides that studying should have a weight of 0.8. Instead, the neuron figures out the right weights by itself, by looking at data. You give it hundreds of examples of students who passed and failed, and it adjusts the weights until they work. We'll get into exactly how in part 3. For now, just know that the weights are what the neuron learns. Let's see what a single neuron actually does in practice. Imagine plotting every student on a graph. X-axis, hours studied. Y-axis, hours slept. Green dots are students who passed. Red dots are students who failed. What the neuron learns is a line that separates the green from the red. Students above the line pass. Students below it fail. This line is called a decision boundary. And this is the key insight about a single neuron. It can only draw a straight line. One neuron, one line. If your data can be separated by a straight line, a single neuron handles it perfectly. This is called a linearly separable problem. But what if the data looks like this? Imagine two classes arranged in a pattern where no single straight line can separate them. Maybe the passing students form a curved region, or the data spirals together. A single neuron is stuck. It can only draw one straight line, and no matter where you put it, some points end up on the wrong side. That's what a single neuron is stuck with. It computes a linear function. In 2 dimensions, that's a line. In 3 dimensions, it's a plane. But it can't learn curves, spirals, or anything nonlinear. You need more neurons for that. Now, you might be thinking, this is just a simple math formula. How does this power something like ChatGPT? The answer is scale. GPT-4 has an estimated 1.8 trillion parameters. Each parameter is a weight or a bias in a neuron. That's 1.8 trillion of these tiny knobs, all tuned together to produce language that sounds human. It's not just language models either. When your phone recognizes your face, that's neurons detecting edges, then shapes, then features, then matching them to you. When a self-driving car spots a stop sign, neurons at every stage of the pipeline. When Spotify recommends a song, neurons comparing your listening patterns against millions of others. Same unit every time, just wired up differently. Before we move on, let's revisit the activation function. Sigmoid was the original choice, but modern neural networks mostly use a function called ReLU. Rectified linear unit. It's absurdly simple. If the input is positive, output it unchanged. If the input is negative, output 0. That's it. No fancy curve, just a hard cutoff at 0. Why does something this simple work? Because ReLU is fast to compute. It doesn't have the vanishing gradient problem that plagues sigmoid in deep networks, something we'll cover in Part 4. And it lets networks train much faster in practice. Most of the AI breakthroughs of the last decade use ReLU or close variants of it. Let's recap. An artificial neuron takes inputs, multiplies each by a learned weight, sums them up, adds a bias, and passes the result through an activation function. It's a tiny decision maker. One neuron can draw one straight line through data. That's useful but limited. One neuron is limited. But what happens when you connect thousands of them in layers? Those straight lines start combining into curves, surfaces, and really complex decision boundaries. A single neuron can't recognize a face or understand a sentence. A network of them can. That's part 2.